We're just going to practice with some derivatives here. So looking at these derivatives, we want to look at what type of rule we're going to use here. So the first one we're going to we're looking at the power rule here. So when we differentiate this, we're going to apply the power, which is 1/2. Okay, so we end up with 3x plus 2, and that power becomes negative 1/2. Okay, so that's going to end up in the denominator. Now, because of that horizontal compression of 3, we have to multiply by 3. Okay, so when we write this out, it's going to be 1 over 6 square root 3x plus 2. So we're just applying the power rule here. Unless it says specifically use definition of the derivative and the limit, we're going to do it using the easier method, using the power rule or whatever rule we have. So this one here, we're going to do, this is a known derivative. Derivative of sine is going to be cosine, so we end up with 3 cosine 2x. The derivative of a constant is 0, so I'll put plus 0 for now, although we don't really need to. And we need to make sure that we apply the times 2 because that's a horizontal compression of 2. So I'm just going to write the times 2 at the end here, plus 0. And so this becomes 6 cosine 2x. Okay, so there's our derivative function. For this one here, we can apply our log rules. If we look at our formula sheet, so I'll give you a second to look at your formula sheet, the derivative of log. Okay, so the derivative of log, when we differentiate log, we're going to do the 1 over the argument. Because the argument is, because the base is not base e, we have to account for that. Okay, so with logs, when we differentiate logs, we're going to divide by log of the base. And because of that 2, we're going to multiply the times 2 because it's a horizontal compression. And then we get plus 0. Now, looking at this, things cancel out. So when we cancel this out, though, it appears that that 2 had no effect in my derivative, which is strange, because if there 2 wasn't there, I'd get the exact same answer. Okay, so there's a couple things we should maybe look at. So first of all, I'm just going to simplify and get the answer here. We're going to end up with 1 over x log 10. Okay, so a couple things we can look at here, and this is really just looking at using exponent properties. And we can actually just use exponent properties to make this life easier for us here. So I could actually use exponent properties to say that f of x is really equal to ln 2x over ln 10. That way we don't have to use that extra divide by log 10 when we differentiate. It just shows up in my, before I even differentiate, it shows up as a constant. So I don't need to do anything with that other than just leave it there, and it just shows up in my final derivative. The other part was, why did this this times 2 end up canceling out? Well, the reason why that cancels out is because if we think of log 2x, we can write this as log x plus log 2 all over log 10. Log 10, I'll just write that as 2 separate fractions here. And log 10 to log 2 over log 10 is really a number. So all this is really a constant. So the reason why that 2 cancels out is because really the horizontal compression can be factored out as a vertical expansion, and then that doesn't affect the graph at all. So this all just becomes a constant, and when I differentiate this now, I do f prime. This is really just 1 over log 10, and then 1 over x. So I just put the x in the bottom. And we end up with the exact same thing we started with, but the derivative was much easier than doing all this stuff here. But it took a little bit of work on the front end to simplify the log first. Now, either way is perfectly fine. Whatever way you find is easier to keep track of, that's the way I would suggest that you do it. But there are alternatives, especially with logs, and I would really suggest converting all logs into base E, just because it'll be much easier to deal with any base E log than any other base. So here we have exponential functions. Okay, the derivative of exponential functions are themselves, and being a base E, it just stays base E. If it was a different base, we'd have to multiply by that non-base E factor. This one is power rule and power rule, and that's it. For this one here, same thing, we just apply our rules to this. This is going to be 2e to the 5x, just regenerates itself, but because of the horizontal compression, I need to multiply by times 5, plus the derivative of tan is secant squared, and I can just simplify this into 10e to the 5x plus secant squared x. There's my derivative.